Hello, I think we're going live. Yes. Let's wait for it to actually work. Okay, yes, we are definitely live. I hope the audio is actually working. So today I'm going to focus on setting up the project for creating my own CPU. In particular, I'm going to use Vivado and probably SystemVerilog. The main idea of the project is to create an OS after I have my own CPU. So without further ado, let's actually start to configure the environment. So I'm going to create a new project in Vivado. But before doing that, I want to actually learn how to possibly create a better structure so that I can upload my files into my GitHub, which I set up here. So yeah, maybe let's see this simple project here. Not finding what I want. Okay, so yeah, first of all we need to create the .gitignore file so that we can not include many of the auto-generated files by Vivado. So let's actually go to coding. Let's go to my CPU. Here we can create a gitignore file. Yeah. I'm going to say that why is it asking for this thing here? Okay, yeah, for sure we're going to put Vivado start. Okay, sure. For the project we are going to call it RZT CPU, of course. Okay. Dot PCL, and then let's also put RZT CPU start. Perfect. Okay, so this is becoming too difficult. For now, I'm just going to create a new project, and I'm gonna save it in the repo. So let's write the CPU. Did I write it like this? No. All capital letters. And also, yeah, this is fine. Okay, and I'm going to put it in my repo. Where is it? Here. So it's going to go in here. Create project subdirectory. Yes. Next. No, we don't have to specify any sources as of now. Yeah, next. Okay, for the board. So is this one? I have the Basys 3 board, which is a very nice board, which apparently is not here for now. So we need to refresh the list, so that is going to download everything. So let's wait. In the meantime, I think I'm going to fetch a few resources on my on SystemVerilog, because I don't know much about it actually. I used to code in VHDL, but I'm not. I mean, I want to try SystemVerilog because I've seen that it's been also quite used in the industry. No. Okay. So there is a tutorial in here somehow. I'm also going to use AI a lot in this project series, because sometimes I can't directly find the answer that I want. But for now I'm just interested in seeing the syntax. Here it is still downloading the board, so that's fine. Okay. Okay. Ciao Angie. Yeah, let's wait. I guess in the meantime I will talk with Gemini. Okay. Wow, this is a huge paper, but it looks like it's very in-depth. So I might start by reading this paper actually. Okay, the meantime here it has finished. Let's see if we can find the basis. We cannot still find the basis board, which is awkward. Just the default AMD part. That's strange. That's very strange. I don't know why I can't find the... No, it's not that one. Okay, it actually crashed. Great. Okay. Great, my Vivado crash just crashed. No. Okay. It's not starting well. Actually, now I don't know if it already generated some files, so I'm going to check. Yes, it did actually. But the folder is empty, so I'm going to remove that. Okay. So let's try again. Let's create a new project. Let's put it in here. Okay. Yes. Next. I can't find the places. That's very strange. Maybe I forgot to actually install the board. Oh my gosh. Oh, of course it's not working right now. Okay, I'm gonna do something in here. Why are the boards not installed? That's why. Yeah, I need to start the boards. Oh, actually they're already there. So what's the problem? Arctic 7 FPGAs. Okay. I don't understand. I can't see the board from the app. Even though it's already there. I mean, even though I added the required board. Let's do this. Basys 3. Yep. Let's open these two files. This should be enough. Should I use VHDL? I'm not sure. Let's see. Next I'm going to assign install Vivado. I already have that. Launch Vivado. Okay. RTL. A partner board must be chosen for the project to target. Yep. If your board does not appear in the list, Digital boards file have not been installed. Okay. Let's do that then. Okay. Cable drivers, I have it. Digital board files. Okay. Done. Of digital. Vivado boards category. Okay. Okay, so first of all, I need to close Vivado again probably because I need to change some of their configurations. So let's close Vivado. Let's also close Gemini for now. Okay, there should be, yes, let's unzip Vivado board files. Okay, oh my gosh, yep, nice. Okay, so let's open files. Let's go to downloads here and new board files. Let's copy everything, and now we need to go in. How can I go up? How can I go to root? You're telling me I can go to root from here? Okay. OPTA, then we need to go to Vivado, but it's not here. No, Xilinx. Same. Xilinx is not here, but Xilinx, if I'm not wrong, is in my home. Yes. Then here, Vivado. I have no idea. Vivado, and then data, boards, board files. Okay, data, boards, board schemas, I guess. No. Let's create the folder board files, and then let's paste everything in here. Ba-bam. Great. Now it should be working. So let's go again. Here. Let's create a new project. In coding, which I cannot find. Yep. RTC CPU. Yep. Next, RTL project. Now, haha, yes. It worked. Base history. Next. Yes. Finally. Okay, so now we have a Vivado project, and I still don't know what to do, because right now we need to first choose what language to use, and I need to consider which architecture to build. So there's a lot of research to be done, and so let's start by the GitHub README. So let's go to coding again, CPU, and let's start editing the README. So for now I'm going to use the README for tracking what I'm doing. When I move forward, maybe it makes sense to switch to some other kind of tracking system, because I cannot fill the whole README for this. But for now, let's write in here. So VHDL or SystemVerilog. So let's start by this. Let's do. I will just quickly ask Gemini on this. Why is that .git ignore gone, by the way? Oh my gosh. Okay. I need to create a CPU. Is it better in VHDL or next or in SystemVerilog? Okay, you can close this in the meantime. Maybe we can open the schematic and give a look at the board. Okay. So let's see what Gemini says. The classic debate. VHDL is the safe choice. Much more verbose. Okay. SystemVerilog studies the industry standard. Most modern RISC-V implementations like Hypax, CV, and Western Digital are within SystemVerilog. Okay. Okay. But it is weakly typed. Okay, I will go with SystemVerilog. Gemini suggests that, but I also wanted to to get a view of how the language works. Something is wrong here, by the way. So yeah, I'm going to go with that. We can close this. We can close this. So probably let's go with SystemVerilog. And let's update our to-do. Paper, and I mean, after we have that, maybe, I mean, while I am reading it, maybe it makes sense to try an example. So implement a small example on debug. We can also, since we are using SystemVerilog, switch the language. Here it says Verilog. But how can I actually change the language in Levato. Okay, so this targets the synthesizable subset of SystemVerilog for ASIC and FPGA design, which is what we want, absolutely what we want. Okay. Data types. Okay, let's see. Okay. Blah blah blah. So this is some history about the language, which I don't really care now. Okay, this is interesting. It shows the different versions of Verilog. So at first it was just this set, and then it gradually became bigger and bigger, with the biggest update with SystemVerilog, which added a ton of functionalities, which is very interesting. They use synopsis, which is okay. There is no official SystemVerilog synthesis standard. Ah. Okay. That's interesting, by the way. So there is currently not a synthesis engine for SystemVerilog. Okay. I mean, is this the case? Let's see. First class citizen for both synthesis and simulation. Okay. Structures. Wow. What? Settings, project settings, general target language. But there's no SystemVerilog, bro. Write a new Vivato ID. Okay, we can try. Save your work and start Vivato. Sure. Exit. Wow, it is very different. I'm not sure I like this, but let's give it a chance. Where is it? Okay. Doesn't change shit. I don't like this view, so I'm going to switch to the old view also. But anyway, I don't know. Don't know why, but I can't see SystemVerilog in here. I'm just going to close it again because I don't like this this view. Let's search online. No, I'm not in here. Okay. So let's put a higher model in here. No, why not? Take one Pro. Okay, so I can just save in .sv apparently. To target SystemVerilog, set file type. Oh, SystemVerilog, okay. Sure. Okay, got it. So here I can. Oh no. No. No, I don't want any Vivat. Apply. Yes, need to close it again. Oh my gosh, I'm never gonna start tonight. No, I'm not here. Okay, finally. Yes. Okay. Great. So we can go on here. Data types. Term value set is used to refer to state values. Okay, and 4 state values. Okay, data types is used as a general term for net types, variable types, and user-defined types. Term value sets and data types are not used in the same way in the official IEEE SystemVerilog standard, which is written primarily for companies that implement software tools such as simulators and synthesis compilers. SystemVerilog standard uses terms such as types, objects, and kinds. Okay. I don't care. Value sets. The original Verilog language has only 4 state values, where each bit of vector could be 0, 1, z, or x, which may make sense. SystemVerilog added the ability to represent 2 state values, where each bit of a vector can only be 0 or 1. Okay. SystemVerilog added the bit and logic keywords to the Verilog language to represent 2 state and 4 state value sets, respectively. SystemVerilog net types, such as wire, only use the logic 4 state value sets. Some variable types use 4 state logic value sets. Okay, while other variables use 2 state bit value sets. So logic can basically be 0, 1, z, or x, while bit is only 0 or 1, which makes sense. There is more to the bit and logic keywords for those that implement simulators and synthesis compilers, but this generalization suffices for understanding how to model design uses SystemVerilog. The bit and logic keywords can also be used without explicitly defining a network variable, in which case a network variable is inferred from context. Okay, interesting. The keyword bit always infers a variable. The keyword logic infers a variable in most contexts, but infers a net if used in conjunction with a modular input or in-output declaration. So, the problem here is that I think he's giving it's getting already for granted that you know Verilog, which I don't. So, but let's see. So input I1, this infers a 4 state net. Okay. Same as here, input logic. This is a module, so I guess it's like an entity in VHDL. But if I do input bit, this infers a 2 state variable. Okay. Output, this infers a 4 state net. Sure. Output logic same, but if I do output bit, it infers a 2 state variable. So whenever you don't put the keyword bit or logic, you get a logic basically. Internal signals with inferred and explicit types. So bit clock, this is a bit, so it's a 2 state variable. Okay. Logic reset infers a 4 state variable because it's a logic, makes sense. Logic, so it's a vector of 8 bits, I guess, infers a 4 state variable. Sure. This is a wire which explicitly declares a net, so it infers a 4 state logic. Sure. for a statement, and this declares a variable. Okay, so it's giving a lot for granted about Verilog, which I don't know and which is not ideal. So I'm not sure if I can actually learn easily from here. I start maybe this one. Okay, I think I'm going to follow here because it looks more structured. Yes, let's fucking ditch this. So, hardware description languages like VHDL and VHDL are used to describe hardware behavior. So it can be converted to digital blocks made of gates. SystemVerilog is an extension of Verilog with many such verification features, allow engineers to verify design using complex test bench structures and random stimuli. Yes, that's VHDL. Why is Verilog not preferred? Back in the 1990s, Verilog was the primary language to verify functionality of designs. They were small, not very complex, and had less features. As design complexity increases, so does the requirement better tools to design verified. SystemVerilog is far superior to Verilog because of its ability to perform constrained random stimuli. It uses object-oriented programming features, which is very interesting. So, what is verification? It is the process of ensuring that a given hardware design works as expected. Yeah. Sure. A hardware design mostly consists of several Verilog files with one top module in which all other submodules are instantiated to achieve desired behavior and functionality. An environment called test bench is required for the verification of a given Verilog design, and it is usually written in SystemVerilog these days. Okay. The idea is to drive the design with different stimuli to observe its outputs and compare it with expected values. Sure. Okay, same as VHDL. So, example. Consider a simple Verilog design of a D flip-flop, which is required to be verified. Oh my gosh. So it's giving also this Verilog for as a starting point. Functionality of DFF is that Q output pin gets latched to the value in D. Yeah, I know, a flip-flop, sure. Oh my gosh. So what? Okay, so apparently SystemVerilog is just used for test benches, I guess. Okay, so let's see what it says. You do not need to learn standard Verilog first. If you learn SystemVerilog, you're automatically learning modern Verilog. Okay. Cool. Okay, I think I'm also going to write a section here with some useful resources so that I can look it up later when I need to. So, resources. What is this? Okay, this one up to dated blog apparently about some stuff. I think he's creating also a CPU. Yep, the zip CPU. Cool. Insert. Super cool. Okay. I'm going to save also this website because it might be useful. Okay, this also looks useful, so let's also save this. ASIC word. And then these are hands-on examples apparently and exercises to learn Verilog, but I'm not sure this is targeting SystemVerilog. Okay, let's see, not sure. Oh my gosh, there's a lot of stuff. Okay, yeah. I'm also going to save this because it's probably it's a website full of information. So HDL leads, and last but not least is this book. Let me see. This one, yes, Stuart Sutherland. Well, this is a huge book too. Let's see if it can be interesting. Yeah, I think it is very interesting. Probably I'm going to study from here. Okay. Okay, so I'm going to download this book actually. Oh, it's coming from ZD. I think I'm gonna cut this part. Yeah, just don't look at it. Okay. Okay, very cool. So, target audience. No. This book is intended to help users that value language at the select of SystemVerilog. Oh my gosh. Oh my gosh. Are they gatekeeping this system? I mean, this Verilog. Brief review of SystemVerilog and key enhancements that it does to the Verilog language. No, it is recommending another book. Free range SystemVerilog. There's no free range SystemVerilog. Really? Teacher design computer architecture. I think I might also have this book actually. I'm not gonna click on these links, but yeah, maybe this book is actually interesting. I think I'm going to sleep shortly because I can't think anymore, but let's see an example of the difference between VHDL and SystemVerilog. So I know how this works. So let's see what happens in SystemVerilog. Always FF. I don't know what that does, but I guess this means that at the positive edge of the clock, this looks like a process. So if reset is 1, I don't know what this B1 is, then set Q to 1, and again I don't know what this bit 0 means, otherwise put Q to D. They're also using these arrows here, which I never understood, but okay. I'm a bit torn if like reading a proper book or just starting with the help of AI. But maybe before I go to sleep I could actually try to do something stupid and see how it works. Yes, let's actually try to see a small example in Vivado. Provide a small example in Verilog. Provide exercises and follow-up questions. I'm going to look at this book later, so I'm going to write this here actually. Wait. Digital design and computer arts risk V edition. Okay. Okie dokie. For now, let's save this, and let's also recreate the .gitignore file which disappeared randomly. No, it's right here. Ah, true. Let's do it. I am stupid. Yes. Oh my gosh. What? Okay, get pull. Oh no. What? Yes. Oh my gosh, what is wrong? What file is here which I don't have locally? Okay, this is very weird. Very weird. Where am I? Yeah. Merge conflict. We need to open VS Code. I don't care. Where is it? Oh no. Okay. No. No. Except but. Yes. Yes. Exactly. Let's do this. Then we can do that. Merge. Push. Done. Great. Okay. Okay, a wire is used to connect elements together. It cannot store a value, it just processes it along. It is ever using combinational logic. A register is just a register. A register can become a flip-flop, but it can also be combinational logic if used inside an always block. What? To bridge the gap from VHDL, think of an always block in Verilog exactly like a process. Okay. This is a 2-to-1 multiplexer within standard Verilog. Okay. So if I bring this here, let's create a file. Create file. Verilog or SystemVerilog. No, Verilog. Looks. Yes. Okay, here we have this mux. The UI is small as fuck. Yeah, let's make it bigger actually. Display. Oh no, I'm not restarting now. Okay, so module mux. Let's call it. Okay, let's call it mux. So inputs y. No. Okay. Okay, so those are the inputs and there are wires. Okay. Input wire cell. Okay, this is another input, of course. And then we have the output, which is a register, and which is Y. But it's interesting that I can finally use this C-like comment. In VHDL, it was the double dash. So this is the output Y. Must be registered because you assign it in an always block. Okay, I regret this here. Cool. Okay, let's try this. Always. So always is the equivalent of a process, a VHDL process. What is this? At start begin if. Okay, and this is the general behavior of a multiplexer. So cool. I have a lot of questions. What the fuck is this shit? Okay, it's cool that I can use a equal. Oh my gosh. And else begin. Right, it was there. And and. Okay. No. Okay, the star, it means trigger this block if any input changes. Okay, so I guess this is the sensitivity list. And what other questions do I have? Yes, what is this? It's this thing here, because that's very strange. Never seen something like that in VHDL. Yes, the add symbol in Verilog is exactly equivalent to the sensitivity list in a VHDL process. It tells the simulator when to wake up and evaluate the code inside block. Always add A or B or cell is exactly like VHDL's process A, B, cell. Okay. Always add star is a modern Verilog shortcut. It tells the compiler, look at all the inputs I used inside this block and automatically create the sensitivity list for me. Oh, okay. It is identical to VHDL 2008 process all. We use this for combinational logic so we don't accidentally forget a signal and create a mismatch between simulation and real hardware. Yeah, okay, this is really cool. For a flip-flop, we would use always add positive edge clock, which maps directly to VHDL if rising edge clock. Cool. What is 1 bit 0? These are Verilog defines literal numbers. Verilog requires you to be very explicit about the width and base of a number to avoid hardware mismatches. The format is always width in bits, then quote, single quote, base value. Let's break this down. So this means 1 is the number. Oh no, the number is exactly 1 bit wide. The base is binary, okay? But if it's binary, we already know it's... Oh no, okay, I got it. And the value is 0. In VHDL, you will just write 0 for a single bit or 0, 0, 0, 0 for a vector. Verilog requires a bit more typing, but it prevents ambiguity. Here are a few more examples to lock it in. Okay, got it. So, without reading, this would be the width. So, 4 bits. It is a binary and it is 1010. Okay, 4-bit binary number. Yes. This is 8 bits. It's hexadecimal and it is the value FF, which is exactly 8 bits. Yes. This is 32 bits. It is decimal and it is 100. Okay, cool. Very cool. Okay. Quite sleepy. I understand the sensitivity list and number formatting. Let's revisit the LU for 1 more exercise. No, I have another question. So, is this actually the way I would declare a multiplexer in SystemVerilog? The short answer is yes. It is perfectly valid SystemVerilog, but it is not the best way to write it in SystemVerilog. Because SystemVerilog is a superset of standard Verilog, any valid Verilog code will compile and synthesize perfectly. Yes. However, SystemVerilog introduces a few quality of life improvements specifically to fix the annoyances you see in that Verilog example. Site. Let's look at the two main differences if we were to write that exact same multiplexer using modern SystemVerilog features. The logic data type. Goodbye wire and register confusion. Okay, in standard Verilog, you constantly have to juggle wire for structural connections and register for variables assigned inside an always block. It is one of the most common source of errors for beginners. In SystemVerilog, you just use logic for almost everything. The compiler is smart enough to figure out if it should be a wire or a flip-flop based on how you write the logic. Okay. Intent specific blocks. Goodbye always star. Standard Verilog uses always add star for combinational logic, but what if you accidentally create a memory element, a latch, inside it? The compiler will just synthesize a latch, often without a strong warning, which ruins FPGA timing. SystemVerilog introduced always comb. This explicitly tells the compiler, I'm trying to build pure combinational logic here. If I write something that creates a memory element, throw a massive error. Okay, super cool. Okay. Always comb. Okay. Okay, I think I'm going to stop here for today because I'm very sleepy. But yeah, so I guess I'm just going to learn by doing about SystemVerilog, and probably maybe in my free time I'm going to read a bit about the language. It looks pretty straightforward. I mean, this was Verilog, but I'm going to try SystemVerilog, and yeah, that's it. I need to decide which architecture to use for the CPU. I think I'm going to target a 32-bit architecture because the FPGA I have is very small, which, by the way, I'm going to show you a bit more, which is this one, which is really fancy, but it has not much memory, so we need to target a small CPU probably. Yeah, I guess for today it's all, and I am going to sleep. Good night.